All right, now that we've defined things like density and mass and volume and things like that, we really need to think about how this is going to relate to us in the class. So really, really important concept. I can't stress this enough. Give it a big star, give it an underline, a highlight, whatever you need to do. In this class, we predominantly talk about flow rates. And these are rates at which material moves from one place to another. So a flow rate implies that this is per unit time. That's critical. So if we talk about mass flow rate, let's use this as an example. Mass flow rate will be mass per unit time. It's not mass itself. So a mass flow rate is not in terms of kilograms, it's in terms of units of kilograms per second. And that's absolutely critical when you look at problems that we do. Okay, so I can't stress that enough. When we talk about mass flow rates, we're going to talk about M with a little dot over it. That dot over it indicates that it's a rate. This is the same as what we call dm dt from calculus. So we could use our derivatives to find rates. We're not going to have equations to take derivatives of, but it is the same as dm dt that you would have learned in calculus. Same thing. We can also have volumetric flow rate. So as you might anticipate, that's a V with a dot. It's volume per unit time. It has units of something like meters cubed per second, and that would be the same as dV dt calculus. So all those calculus courses you took, they are important, right? Because we are talking about derivatives in this class. We're not necessarily taking derivatives the same way that we would in a calculus class, but we actually are talking about rates, and that's really, really, really important. So let's turn over. And let's use the top of this page to just draw a little diagram to hopefully help you out with this. So let's say that we have a pipe, right? And we have an area that things can flow through in this pipe. So we're flowing in and we're flowing out. So when we talk about mass flow rates, if this is a fluid in the system, right? You can label it as a fluid to remind yourself. The fluid has a mass flow rate, an m dot, of kilograms of fluid per second, and it has a volumetric flow rate of something like a meters cubed of fluid per second. So that's really, really critical. Many times in the real world, it's actually easier to measure volumetric flow rather than mass flow. And that's really critical, right? We can measure the amount of volume that moves through a pipe, but it's really hard to measure mass because there could be many things there, right? There could be a fluid that's carrying particles, and that's harder to get the mass. But we can definitely find the volume. So one critical thing that we care about with this statement right here is we know that density equals mass per unit volume. We can also say that density is mass flow rate per volumetric flow rate because your units of time will cancel. So why is that important, right? If it's easier to measure volumetric flow rate, but maybe we want to do things in terms of mass flow rate, we can measure V, use density to get M, right? M dot and V dot. Let's make sure those are rates, right? So that's really, really critical, right? Because we can measure volume in the real world. We can find the density of whatever we're mentioning, and then we can get a mass flow rate. And the reason that we care about mass flow rate, right, is that mass is always conserved. You can't create or conserved, there we go, destroy matter, right, or mass. That's one of Newton's laws that you hopefully learned in physics. You can change the volume of something, but you can't change the amount of mass, which is why we can do mass balances, right? So this is going to be really critical going forward. All right, let's test your understanding. So this is a great place to pause the video and try to answer this question. If we have a mass flow rate of N-hexane that has this specific density right here, or just density, not specific density, in a pipe, and it's moving at this mass flow rate, what is the volumetric flow rate? So take a pause and see if you can solve that. All right, hopefully you paused that video. We know that density is equal to mass flow rate divided by volumetric flow rate. So if we're trying to find the volumetric flow rate of something, we can rearrange that equation to say that the volumetric flow rate is equal to the mass flow rate divided by the density. We have both of those numbers. We have 6.59 grams per second. So that's a mass flow rate if you look at the units. And then we can divide that by 0.659 grams per centimeter cubed, which gives us a volumetric flow rate of 10 centimeters cubed per second. Hopefully you got there, and if not, hopefully you can see how we got there. And do a quick check, right? When you get an answer, look at these units. Are those units of volumetric flow? Well, we have a volume, centimeters cubed, per unit time, seconds. So yes, that is a volumetric flow rate, and that's real important. All right? So out in the real world, we do have to measure flow, so sometimes it's nice to know how we can do that. We have two types of flow meters. We have what's called a rotometer, and a rotometer is a tapered vertical tube with a float. It tends to have, as you have a larger flow rate, the float goes higher in the tube. So there's two pictures down below. The one on the left is the rotometer. So you can see here's the little float right here, kind of colored it in pink. And we measure how high it goes based on flow rate. The other type of flow meter that we can have is what's called an orifice meter. And so by process of elimination, that's going to be the one orifice meter on the right. And that measures a pressure drop across an orifice. So a larger flow rate is a larger pressure drop. So this is an orifice plate right in here. And as you go through, it measures in this manometer down here the change in pressure over time. So just kind of for your knowledge, so you know how this is done out in the field. After this, we're going to talk about chemical composition. Make sure that you understand this concept up above, the fact that we can use volumetric flow to get mass flow. That's really important. So just make sure that that's really clear before you move on.